Hello, focused learners. Welcome to this absolutely crisp, detailed HD explainer. Today, we are going to decode one of the most fundamental concepts in all of mathematics, the intersection of sets. If you've ever felt like math is just too abstract, that's about to change. We're going to take those dense textbook definitions and completely transform them into crystal clear visual logic. So get ready, keep that focus locked in, and let's master this concept together.
Okay, let's dive into this. Here is our highly structured roadmap for today so you know exactly where we're headed. We'll start off by establishing the common funda. Then we'll visualize everything using Venn diagrams. After that, we'll decode some illustrative examples, look at the twist of the empty intersection, and finally, we'll master the 6 golden rules. Let's go.
So moving right into our first block, section 1, the common funda. Let's really understand the core of this.
Sets are literally the building blocks of math. But what does finding their intersection actually mean? Well, the textbook tells us that the intersection of two given sets, let's call them set A and set B, is the set of elements which belong to both set A and set B. Simply put, we only care about the common members. An element only makes the cut if it lives in A and also lives in B.
And this brings us to a super simple yet incredibly powerful takeaway. Intersection is fundamentally an "and" idea. If anyone asks you the essence of intersection, just remember that one word, and. The element must be in A and in B. There's no or here, no options. It's a strict, absolute condition. It has to be a part of both sets to be included.
So how do we write this in math speak? Symbolically, A intersection B is equal to the set of all x such that x belongs to A and x belongs to B. See that symbol that looks kind of like an upside-down U? That is our intersection symbol. We read it out loud as A intersection B. Whenever you spot that symbol, the word "and" should instantly flash in your mind.
All right, section 2, understanding through Venn diagrams. It's time to visualize the logic. Let's move from abstract text to a crisp HD visual representation. And this brilliantly illustrates the whole concept. Imagine 2 circles, set A and set B, sitting inside a large rectangle, which represents our universal set U. I want you to focus purely on that shaded portion, right where those 2 circles overlap. That little leaf-like structure right in the middle, that is exactly A intersection B. It's the precise territory that belongs to both circle A and circle B.
Moving right along to section 3, illustrative examples. Let's decode the math with some real applications.
Now it's time to put this definition to the test. Think of this first example kind of like a puzzle. In set A, we have the factors of 18, which are 1, 2, 3, 6, 9, and 18. In set B, we have the factors of 24. Now, channel your inner detective and compare these 2 lists. Which numbers are sitting there in both lists at the exact same time, perfectly satisfying our "and" condition?
You guessed it. A intersection B gives us a brand new set, 1, 2, 3, and 6. These are the only 4 numbers that perfectly match across both sets. 9 is in A, but not B, and 4 is in B, but not A, so they just get rejected. We only select the common members. It's totally simple, logical, and straightforward.
Let's level up slightly and look at another example from our source. Here, the sets were defined by inequalities first. Set A was natural numbers strictly between 1 and 6. So, set A becomes 2, 3, 4, and 5. Set B was natural numbers strictly between 2 and 9. That gives us 3, 4, 5, 6, 7, and 8. Take a really close look at these 2 lists. So, the crucial point here is the common elements are simply 3, 4, and 5. The results for A intersection B is just this small 3-number set. Because no matter how complex the definition of the set initially looks, at the end of the day, we are quite literally just extracting the matching elements.
Okay, let's make things even more interesting. What if the sets are infinite? Here, set A contains all multiples of 2, represented as x equals 2n for any integer n. So that's -4, -2, 0, 2, 4, and so on forever. And set B is the multiples of 3, stretching out infinitely in both directions. What on earth do these 2 massive lists have in common?
And here is a great mathematical aha moment. When you intersect the multiples of 2 with the multiples of 3, the common elements drop out as -6, 0, 6, 12, and so on. Basically, they're the multiples of 6, because any number divisible by 2 and divisible by 3 is obviously going to be divisible by 6. See? Intersection handles infinite sets perfectly too.
Now for section 4, the empty intersection. Let's look at zero overlap scenarios.
Let's introduce a little twist to the story. What happens if two sets have absolutely nothing in common? This is a fun brain teaser for you. What is the intersection between the set of odd natural numbers, like 1, 3, 5, 7, and the set of even natural numbers, like 2, 4, 6, 8? Is there literally any natural number that fits into both of those categories? You're spot on. There is absolutely no number that is both odd and even. Therefore, their intersection is denoted by phi, the empty set. It means that in a scenario like this, the intersection is totally null. If you drew this on a Venn diagram, the two circles would never even touch, meaning there's zero shaded region.
Let's grab a geometry-based example from the source to prove this isn't just about lists of numbers. Imagine set A contains all the points on a circle, and set B contains all the points on a different concentric circle. Concentric just means they share the exact same center but have different radiuses. What do you think their intersection is?
Well, since concentric circles never cross or even touch each other, they can't possibly share any common points. So once again, the answer is the empty set, phi. This just proves that the fundamental logic of intersection, whether you're looking at lists of numbers or shapes in geometry, always stays exactly the same.
All right, let's move to our final section. Section 5, the 6 golden rules. Let's look at the mathematical properties of intersection. Just like addition and multiplication, mathematical set operations have their own rules. Let's break down the first 3. First up, the commutative law. A intersection B will give you the exact same result as B intersection A. The order just doesn't matter. Second, the associative law. If you have 3 sets, whether you group A and B first or B and C first, the final common elements won't change. And third, the idempotent law. If you intersect a set with itself, well, the common elements are just the entire set A itself.
Now, what's really interesting is how these remaining 3 laws represent the absolute peak of this logic. The law of phi says that intersecting any set with an empty set leaves you with an empty set. Makes sense, right? The law of U says if you intersect set A with the massive universal set U, you're just left with set A, because A is already entirely inside U. And finally, the subset rule. If set A is a smaller part, or subset, of set B, then their intersection is simply going to be set A.
We have covered the mathematical laws, we've analyzed Venn diagrams, and we've decoded plenty of examples today. But if you only remember one single thing from this entire HD explainer, make it this. The ultimate takeaway is that intersection is always the and condition. Whether you're dealing with infinite equations, natural numbers, or geometric shapes, you are just looking for what exists here and exists there. To wrap things up, I'm going to leave you with a provocative question to really connect the dots in your mind. Based on the law of U and the idempotent law we just went over, if the universal set U contains literally everything, what is the intersection of U and another universal set U? Just think about it. What could possibly be common between everything and everything? Keep pondering that, stay focused, and keep learning.